Hello and welcome to week 9 of live session for spread spectrum communication and jamming. So today actually I am a bit ill, so I won't be able to speak very loudly. If you have any doubt, you can ask me, and those who are watching a recording, then they can drop a mail if they have any problem. Uh, for now, we will be today covering the concept of fading for wireless communications. So, as we know, wireless communication is made out of three composite parts. One is the transmitter, one is the receiver, and one is the propagation channel. So, the propagation channel is the intervening medium between the transmitter and receiver. It can be free space, it can be air, it can be some environment with blockage, it can be some wall, tree, anything. So all that is between the two communicating devices is together cumulatively called channel. So a transmitter, a channel, and a receiver. So propagation channel means it is and the radio channel. So propagation channel is basically when you just consider from the beam point of view, then it is a propagation channel. So the beam is emanating from the antenna and it is being received at another antenna. So between that, the beam traveling path, that is the propagation channel. Whereas the radio channel is the and propagation channel plus the two antennas. So if you include the antennas, it is the radio channel. Now, how does the beam propagate? The beam propagate in three ways. Apart from the direct line of sight, there is a direct line of sight sometimes, but sometimes that direct line of sight might be blocked. Say there might be some blockage in there. So this is like the line of sight. So yeah, so this is the line of sight, but sometimes it may be blocked. Say there is a tree in between the transmitter and the receiver. Then it is a propagation, then the line of sight is blocked. Then how does the beam travel? Say there are buildings here. There is a building here. So the beam will hit the surface of this building and will be reflected back to the transmitter. That is reflection. Another mechanism in which it travels is scattering, in which it goes like this, hits some molecular particle and scatters, like in all direction like this. And another is diffraction. Diffraction means when it goes around sharp edges. Sorry, not like this. When it goes around sharp edges. So like this. So like this. This is like a diffraction. So there are three propagation mechanisms. So mostly we will be focusing on this. This will be known as non-line of sight. So there is a direct line of sight and then there are non-line of sights. So if there are the beams are traveling in free space and there is no blockage, there is uninterrupted LOS, then uninterrupted LOS, then the power received at the antenna receiver is basically given by the freeze equation. This is the freeze equation. FRIIS, freeze equation. So freeze equation gives that your received power will depend on your transmit power proportionally. GTGR are the gains of the antenna. So PR is your received power, GTGR are your gains of antenna. D is the antenna aperture size. So the size of the antenna reflecting size of the antenna transmitter receiver. That is the antenna aperture size. That is D. And L is the some constant which is like a non-ideality constant or something. So if like or proportionality constant you can say. Okay. And then there is lambda square. It also depends on lambda square by d square. So it falls off inversely with distance, that is the attenuation, and it is also directly proportional to the square of the effect, that is, it is inversely proportional to frequency. So the higher the frequency you go, the more the attenuation is. So normal sub 6 gigahertz will have attenuation, but millimeter wave will have even higher attenuation, like that. So that is what is specified by lambda square. So lambda square basically means frequency. If you increase, your attenuation will increase, your received power will decrease. So next, there are large scale effects and small scale effect and polarization. So large scale effect means path loss. So like the equation you see here, this clearly indicates path loss. The more path it, the more path it covers, the more attenuated it becomes, the less received power it gets. Next, there is shadowing. Shadowing happens because of the multipath, and we will talk about that. There is small scale effects. Now, small scale effects are mainly because of multipath. So there is flat fading. It is small scale effect is also called fading. So it is flat fading, frequency selective fading, slow fading, fast fading. And then there is polarization, like horizontal beams are polarized horizontally, vertically, or circularly. So that is, polarization won't be covered here. Mostly large scale and small scale effects will be covered. So large scale, actually there is not much to cover. This is the path loss that we encounter. So that is that is what you will see in large scale. But in small scale, there is flat fading, frequency selective fading, slow fading, and fast fading. So small scale fading or fading is used to describe the rapid fluctuation of the amplitude of a radio signal over a short period of time or travel distance, so that large scale path loss effects may be ignored. So if it is going for kilometers, of course there will be a path loss due to which power will be reduced. But if you take, let's say, a few meters, say 50 meters or something, then the path loss difference in D and D plus 50 will not be that significant. You can say that there are no path loss because the 2 points are relatively close. The path is effectively very small. But even in that small path, even if there is no large scale fading, what you get is small scale fading. Small scale fading is usually called fading. Large scale fading is usually called attenuation. So small scale fading or simply fading happens because of the rapid fluctuation of amplitude over a short period of time or travel distance. As time is, the time period is directly proportional to wavelength, so time and travel distance, any one you can specify. Now, why does this happen? The large scale path loss happens because of laws of nature, that any electromagnetic beam traveling will suffer inverse square loss. That is a fundamental law of nature. But why does some small scale fading happens? See, even if you have line of sight or you don't have line of sight, you will always have large scale fading. If a beam is traveling in physical distance, it will have large scale fading no matter where it is in the universe. It will have attenuation. But small scale fading is non existent when there is only and only a direct line of sight and there is no significant non line of sight. Say you do a communication in the surface of moon. In the surface of moon there is not much in terms of multipath because there are no reflectors. It's just vacant space. So only path loss you will encounter. Path loss traveling through space. Only that you will encounter. Whereas if you are taking the same communication apparatus to an urban environment, there will be buildings, there will be trees, there will be shops, malls, car parking, station, airport, lots and lots of factors which influence the which create multipaths. So if multipaths are created, so the same beam is coming directly, may or may not come directly, and is coming via multiple routes by reflection. Now these paths together when they converge, they can either be constructive or destructive depending on the phase. If they are constructively interfered, they will add up. If they are destructively interfered, they will subtract from each other. But this will cause, because it can either be addition or subtraction, so it is not a monotonic loss like you have free space path loss, which is a monotonic loss. The further you go, the more loss you get. But here the signal can go up and down. It's not only down. Large scale fading is the only direction is down. The moment it leaves transmitter, the power will only decrease, it will never increase. But here in small scale fading, the power, even though minutely, increases and decreases. It increases and decreases because the multiple paths that are coming in, they are changing. The environment around is changing. So the multipaths are changing, their phases are changing. So at one moment it might be constructive interference which makes the signal value bigger, whereas at another point it might be destructive interference making the signal value smaller. So this will create a random fluctuation and these multipath waves will thus cause small scale fading. Now also this is one aspect, delay aspect. Another aspect that happens is the Doppler aspect, that the receiver or the transmitter or both of them might be moving. So if there is a relative velocity established between them, we know that the frequency shift is directly proportional to the relative velocity. So delta F equal to V cos theta by C. So the frequency shift is directly proportional to the velocity of relative velocity between the Tx and Rx. So if the Tx and Rx have a significant relative velocity amongst themselves, then we will have Doppler, significant Doppler. Now with that, what will this Doppler do? This Doppler will change the carrier frequency. Just like multipath was changing the amplitude, the Doppler will not change the amplitude, it will change the frequency. And yeah, and another is time dispersion or echoes caused by multipath propagation delay. This is what happens when one signal arrives directly and another signal arrives after bouncing off 4-5 blockages. So if it is bouncing off 4-5 obstructions, it will of course have a delay as compared to the line of sight signal. So there will, because it has traveled more path, there is a path difference. That path difference will lend itself to phase difference. When there is path difference, there is time difference, and that time difference will make phase difference. So you get the same signal but in a amplitude shifted and phase shifted version. Now this is called an echo. So at the receiver you will receive lots of such echoes. So that is called time dispersion. So these three, the rapid change in signal strength, random frequency modulation due to Doppler, and time dispersion. These are the three effects that make that make the multipath effects in radio channel. These three together combined creates temporal variations by the receiver. So the signal varying with time. So previously, say the signal had a fixed amplitude, fixed carrier frequency, but the signal was varying with time. Now, so previously, what was happening is so previously what was happening was you are sending say xt is equal to a cos 2 pi f t plus phi. So here you knew that even if the signal itself is varying with time, the parameters of the signal is static. Signal varying with time, but signal parameters remain constant. Now, after fading, what happens is because of multipath dispersion, your amplitude is changing, it's fluctuating at every instant of time. After multipath and Doppler, so if you inject both delay and Doppler into this signal, what we will get is xt is equal to at because of multipath. This will be because of cos, and this will be because of Doppler. So the two fundamental parameters of the signal, the amplitude and the carrier frequency, will now both be not constant. So as we were saying that the amplitude and carrier frequency. Okay, so as you can see that the amplitude and frequency will now vary with time because of fading. So there are two kinds of fading, really. One that affects the amplitude and one that affects the frequency. One that is due to delay, one that happens due to delay, and one that happens due to Doppler. So delay wise, there are two kinds of fading, that is flat fading and frequency selective fading. If the bandwidth of the signal is less than the bandwidth of the channel and the delay spread is less than the symbol period, then you will have flat fading because all the symbols, even if there is delay, the symbols will come. The various versions of the symbol will come. Then, before the year ends, before the symbol ends. So within the symbol duration only all the versions of the symbol will come. So it won't happen that when it is, say, the receiver is processing the third symbol. So what happens is that if you say you are processing the third symbol and because the delay spread is high, all the versions of the third symbol from all the multipaths have not come yet. Some versions of the some versions of the multipath is still pending while you have started processing fourth symbol. Now, when you are processing fourth symbol and suddenly the third symbol's delayed version comes, you will process it as the fourth symbol, which will obviously create errors. So that is the reason why you will have frequency selective fading. Now in frequency selective fading, what happens is some frequencies are affected by this fading more than the others. And this happens when the bandwidth of the signal is more than the bandwidth of the channel and the delay spread is more than the symbol period. Then what happens is that you will experience frequency selective fading, which will affect some frequencies or which will affect the frequencies unequally. So that is the nature of small scale fading based on multipath. Now, based on the Doppler spread, there is fast fading and slow fading. Fast fading happens when the relative velocity is pretty high. So, you assume that for a particular time that you are processing the symbol, your channel is constant. But because of high Doppler spread, it might happen that your that time which you assume the channel is constant. This is called the basically the coherence time. That coherence time is lesser than the symbol period. So what happens is that coherence time, the time for which the channel remains constant, is not even one symbol period. If the time period is not even valid for one symbol, if the channel is not even constant for one symbol period, different the symbol will experience different channel throughout its uh, yeah, throughout its time duration. So that is why it is said that coherence time, that is if coherence time is less than symbol period, the channel is varying too fast and your signal cannot handle it. That will create fast fading. And slow fading means that is low Doppler spread, coherence time is greater than the symbol period, and the channel variations slower than baseband signal variation. This will create slow fading. So slow fading means the relative velocity of the transmitter and receiver are less is less. So you have your channel is not varying very fast. Your channel is varying after one symbol has been completely processed. Coherence time is greater than symbol period. So you will experience slow fading, which is not as severe as fast fading. Okay. So how do you measure these spreads? Two effective measure is time dispersion. Rather, four effective measures are there. One is the RMS delay spread or the maximum delay spread. So, to what extent is your signal getting delayed? The copies of your signal rather getting delayed. So that is your delay spread. So that delay spread, you calculate the max or the RMS of that delay spread. That is one parameter. Another parameter is the coherence bandwidth. Coherence bandwidth means the frequency in which you will experience flat fading. So if you give signal higher than this bandwidth, means signal occupying frequencies above this bandwidth or below this bandwidth, you will more than this bandwidth. If the signal is occupying more than the coherence bandwidth, what will happen is you will experience frequency selective fading. But if you stay within the coherence bandwidth, you will experience flat fading, which is much more easier to handle. Similarly, from the frequency domain, there is Doppler spread, that is the maximum spread of the frequency, carrier frequency that happens, or the RMS of the carrier frequency spread. So that is known as Doppler spread. And that Doppler spread will give rise to its own coherence parameter called the coherence time. And the coherence time is basically the time for which the channel can be assumed to be constant. So for that time period, channel will not change. So the parameters of the multipath are this time dispersion parameter, coherence bandwidth, Doppler spread, and coherence time. So we will cover these parameters one by one. So time dispersion, in order to compare different multipath channel and to develop some general design guideline, we find parameters that quantify the delay. So some of the parameters, all of them are basically related to delay. It's just that how you calculate that delay. So based on that, you have mean excess delay, you have RMS delay spread, and excess delay spread. So and you get all these from the power delay profile. The power delay profile is basically the signal power you are receiving at various time instances. Now, the mean excess delay. So here you can see a power delay profile. So at 0, you are supposed to get the line of sight. So the signal you are receiving at 0, that is your 0 dB, that is your reference line. All the power that you will be getting henceforth will be based on the this line, this reference. So after 0, you see that the mean excess delay is the first. So the first parameter is the mean excess delay. It is the first moment of the power delay profile. So now you take all the powers and all the delays and you do an average, weighted average. So the weighted average will give you the mean excess delay. The RMS delay spread is the square root of the second central moment of the power delay profile. So now you have the power delay distribution. You take the second central moment, that is from the mean. Okay, so basically it's the standard deviation of the delay profile. And next, the maximum and excess delay spread, maximum excess delay. So basically, you this excess is defined along a threshold. So whenever you are getting 0 dB at the 0th instant, because you are defining it to be 0 dB. So whatever power you are getting at 0 instance, at the instance of the 0 dB, at that instant the power you are receiving, that is 0 dB. So you will see that I will tolerate up to 20 dBs below that power. Now you will of course get theoretically infinite reflections. So you will get power till t equals to infinity. However infinitesimally small the power. But we cannot process all that power. So what we will do is we will define a threshold and we will say that all the power that is 20 dBs below what has been received at the first instant, all the power that is 20 is accepted, but any power that is more than 20 dBs below the power received at t equal to 0, tau equal to 0 will be treated as noise. So if you define that threshold to be 10 dB, then you can see that the maximum excess delay. So basically, when it starts, when it last goes crosses 10 dB. So this lobe is the last instance of this power crossing 10. So the maximum excess delay, if you define 10 dB as your threshold, is 84 nanoseconds. Okay, so that is how you define excess delay. Now, to quantify the same delay spread in frequency domain, what we will do is we will Fourier transform the delay spread to get the coherence bandwidth. Okay, so coherence bandwidth is basically the description of the delay spread in the frequency domain. So coherence bandwidth is used to characterize the channel in the frequency domain. The RMS delay spread and coherence bandwidth are inversely proportional to one another. So the more the delay spread, the less is the coherence bandwidth. So if you have less delay spread, you will get more usable bandwidth. So you can adjust the threshold according to that. Whatever coherence bandwidth is needed, you have to adjust your threshold of detection. That is, whether you will accept all signals that is up to below 10 dB of the original signal or up to below 20 dB of the initially received signal. You have to decide that based on how much coherence bandwidth you want to have. So the RMS delay spread and coherence bandwidth are inversely proportional to one another. Coherence bandwidth is a statistical measure of the range of frequencies over which the channel can be considered flat. In other words, coherence bandwidth is the range of frequencies over which two frequency components have a strong potential for amplitude correlation. So, if the coherence bandwidth is defined as the bandwidth over which the frequency correlation function is above 0.9, then coherence bandwidth comes to be 50 times the excess delay spread. So delay spread and coherence time. Now, Doppler spread and coherence time. So similarly, one kind of multipath effect is the one kind of rather small scale fading effect is the multipath, and another kind of small scale effect is the Doppler spread. This Doppler spread exists when there is a relative velocity between the transmitter and the receiver, which causes the carrier frequency to shift. This apparent shift in carrier frequency causes dispersion in the frequency domain. So, if your signal was previously between f plus b to f minus b, now it will be between f plus delta f plus b to f minus means f plus delta f minus b. So your frequency is getting spread by 2 into delta f, where delta f is your Doppler spread. So you are occupying more frequency. Now, Doppler spread and coherence time are the parameters which describe the time varying nature of channel in small scale. Now, Doppler spread is a frequency parameter. So, if you want to convert it into a time parameter, you have to calculate the coherence time. The coherence time is the time domain dual of Doppler spread and is used to characterize the time varying nature of the frequency dispersiveness of channel. So the Doppler spread and coherence time are inversely proportional. Just like coherence bandwidth and delay spread was inversely proportional, similarly Doppler spread and coherence time are inversely proportional. So coherence time is actually a statistical measure of the time duration over which the channel impulse response is essentially invariant and quantifies the similarity of channel response. So basically, coherence time is the time at which you can say channel is constant over frequency. The channel is not changing. So this is your coherence time and you have to transmit within coherence time. Different transmitted signals will undergo different types of fading depending on the relation between the signal parameters and the channel parameters. So whether your bandwidth is greater than coherence bandwidth, whether your symbol time is greater than the coherence time. So the coherence time value is a channel property that cannot alone decide what fading the signal will undergo. That is decided by the comparison of the signal parameter and the channel parameter. So with multipath, delay spread leads to time dispersion. That is, you receive at various times. So your in time domain, your signal is getting spread out compared to getting a single impulse at a particular time. You are getting multiple impulses, so across time. So your time is getting dispersed, and at the same time, different frequencies. Because of that, the dual of this effect is that different frequencies will undergo different amount of fluctuation. So time dispersion and frequency selective fading. Whereas Doppler spread leads to frequency dispersion, because now the Doppler shift will change your effective bandwidth, because the carrier frequency will be now f plus delta f. So you will be occupying a space that is 2 into delta f times more than the actual frequency, and this will also lead to time selective fading. That is a different symbol, because it is a highly mobile system. Different At different time instants, the signal will experience different amounts of fading. The two propagation mechanisms are independent of each other. If the mobile radio channel has a constant gain and linear phase response over bandwidth, which is greater than the bandwidth of the transmitted signal, then the signal will undergo flat fading. Class niche. If the mobile radio channel has a constant gain and linear phase response over a bandwidth which is greater than the bandwidth of the transmitted signal, then it will undergo flat fading. In flat fading, the multipath structure of the channel is such that the spectral characteristic of the transmitted signals are preserved. So basically, if you send a signal that does not have a bandwidth higher than the coherence bandwidth of the channel, then all the frequencies will undergo same amount of fading. This will be known as flat fading. In flat fading, the multipath of the channel is such that the spectral characteristic is preserved. So your frequency distortion will not happen. Only your signal will get attenuated. So it is much easier to handle with a repeater or some kind of implement that will boost the signal power. Now there is frequency selective fading, which affects different frequencies differently. So when your bandwidth is more than the coherence bandwidth, then your signal will undergo frequency selective fading, which will lead to different attenuations at different frequencies. And because there will be heavy signal distortion, because the particular frequency components will have different values at different frequency components will have different values at the transmitter and at the receiver. So that will create some frequency selective is fading, and as an effect, the dual effect is that it will create intersymbol interference, because the fading is due because the multipath will create time dispersion, and because of time dispersion, one symbol's content might overlap onto another symbol's content. This will create intersymbol interference, or ISI. Similarly, in the frequency domain, during the Doppler spread, you will get fast fading and slow fading. If the relative velocity high, you get fast fading, and because your velocity is so high, your coherence time will be your symbol will change faster than the coherence time, and you will get a fast fading, where different time instances of the signal at different time instances will experience different amount of fading. In slow fading, the channel impulse response changes at a rate much slower than the transmitted baseband signal. That is, the coherence time of the channel is later than the symbol period. In this case, the channel may be assumed to be static over one or several reciprocal bandwidth intervals. So, because now in slow fading, the relative velocity is low, so your channel is mostly constant over the symbol duration, because your symbol duration is lesser than coherence time. So the channel can be assumed to be static. This is so slow fading, of course, does not affect the signal as severely as a fast fading does. This is a memory map to understand fast fading, slow fading. So if you are exceeding coherence time, you will get fast fading, and if your symbol duration is less than coherence time, you will get slow fading. But similarly, if your excess delay spread is more than the coherence bandwidth, you will get flat slow fading. Less, and if it is more, so this is in terms of delay spread, so you think of the inverse, that is coherence bandwidth. So this side is less, this side is more. So if your coherence bandwidth is more less, you will get flat. If it is more, you will get frequency selective. So these together, so if your delay spread is lower than the if your delay spread is low, you will get frequency selective. If your delay spread is large, you will get flat fade. So anyways, this is really in terms of frequency, the same thing about the frequencies. Now to and to counteract this fading, there is a concept of diversity. So yeah, we can take a 5-minute break and then we will come to the concept of diversity. Okay, so now we come to diversity. A diversity scheme refers to. Okay, so a diversity scheme is basically when you have multi-paths. So what you do is, because these multipaths might do destructive interference, what you do is you send same copies of the signal. Yeah, you send same copies of the signal and they are added together so that if even one of them experiences heavy fading, the the other two might, the other paths might not. So here you can see the, like say you are sending three signals, three copies of the same signal. So you will see one copy will be heavily faded, but the other copy might follow another path because it is released from another antenna. So it might follow another path, and in that path it might not encounter as many interferences and blockages. This will lead to more accurate signal reproduction at the receiver. So basically, you are sending multiple signals and hoping that one of them will not experience heavy fading. At least one of them will not experience heavy fading. So this whole process is defined as described as that the power that the multiple independent signal paths have a low probability of experiencing deep fading together. So if one of them gets deep faded, one another might survive and you will get relatively less fading at the receiver. So that is diversity. So diversity is of two kinds. One is the macro diversity, where you are basically mitigating the effect of straight up blockages. So some paths might offer straight up blockage. So in that case, in that case, in that case, you have to do macro diversity. So you will send in a radically different path so that you can avoid the particular blockage. Whereas micro diversity technique will have less difference among the signals, but are only equipped to handle multipath fluctuations and not entire. Now, another way of classifying the diversity techniques is based on the location. So, if the diversity scheme is applied at the transmitter, it is known as transmitter diversity. So, example, transmit maximum ratio combining. And another is a receiver diversity, which is employed at the receiver. Now, another way of classifying diversity is time diversity. That is, how are you distinguishing the multiple copies of the signal? So, one way I said is space diversity, that is transmitting by multiple antennas. That is what is used in MIMO communications. But if you do not have multiple antennas, then you can employ other ways. It's time diversity, in which the same signal is first transmitted, then you wait for a while, and then you again transmit. and then you wait for while, then you again transmit like this. But if you're trying to DV diversity, so you experience say that whatever was causing multipath a few seconds ago will not cause multipath now. So that is the hedge that you are relying on. But it is not a very good hedge because usually the things that create multipath are static. So unless you are moving very fast, they usually persist throughout time slots, especially if you're static or if you are especially if you're static. Now next is frequency diversity. In frequency diversity, you are transmitting the same signal and multiple frequencies. So the carrier frequencies are changed. Similarly, angle diversity means you are sending the beams at different angles. One is going up, one is going down. And last is polarization diversity, where you do vertical polarization and then horizontal polarization for multiple waves. So they are polarized differently in space, and you expect that the amount of polarization, so vertically polarized wave experiences, the amount of fading it experiences will not be the same as the amount of fading horizontal. Now, next is space diversity. Space diversity, as I have said, is implemented using multiple transmit or receive antenna. So you have multiple antennas, they will give transmit the signal in multiple paths. So the various signals will have a path difference amongst them, and that way you will have space diversity. So coherent combining of the diversity signals leads to an increase in SNR at the receiver than that what would be obtained at a single receiver antenna, because you are getting signal from multiple antennas. So if you can coherently combine them, if you can combine them in a way which does not interfere with other, yes, if you can which does not destructively interfere with the other waves, then you can have an SNR that is higher than the actual SNR. But space diversity also requires the separation between antennas such that the fading amplitude correspond to each antenna are approximately independent. So they have to be well spaced apart to follow independent paths. If they are nearly co-located, so of course you will not have path diversity. So in a uniform scattering environment with isotropic transmit and receiver, the isotropic means antennas which transmit on all sides equally. The minimum antenna separation required for independent fading on each antenna is approximately 100, that's 38% of the wavelength. So they have to be at least separated by 38% of the wavelength for them to count as independent waves. Now, most modern day communication antennas, of course, do not use isotropic because it wastes energy. So, instead, they use sharp beams, and that will have a different fading antenna separation minimum. Now, receiver diversity, independent fading paths are associated with multiple receiver antennas or multiple receiver antennas. So all those multiple fading paths, the diversity that you created, they are received at the different receiver antennas, and then they are processed differently. They are given different weightages. So by changing the weightage assigned to each of the path, you can change the SNR that you are receiving. So here you are changing the weightage given to each path that has come. This is the how you get receiver diversity. So when you are combining multiple signals, you have to ensure that they are in the same phase so that 100% of the energy is combined coherently. There is no wastage of energy. So if they have the same phase, they will simply be added. It will be arithmetic addition. Whereas if they have different phases, the effective the effective will be signal power received will be less. Now there are two types of performance gain associated with receiver space diversity, which is array gain and diversity gain. Array gain is what you get. Array gain is what you get by combining the beams at the multiple antennas of the transmitter. So you are saying combining them, then you will get an array gain. And the diversity gain is when you are combining independent paths that have been received. Okay. Now maximal ratio combining means the signals first have the signals all of them will be weighted relatively, and all the weights are will be non-zero, and the signals will need to be co-phased. That is, all the signal phase detection has to be done and their phases have to be brought together. So if one of them is the reference phase and another is 30-degree off, then you have to multiply by e to the power j 30 degree so that you can get co-phased signals. If you get co-phased signals, you will you okay, the output of the SNR combiner is this same phase, then they will combine maximally. Now the optimal weight calculation, if you do, it will be all the received signal square divided by n naught. So n naught is your noise. So the optimal resulting combiner SNR is basically the sum of the received signal square, summation of Ri square divided by n naught. Okay. Now rake receiver. In fading environment, the principal mean for direct sequence system to obtain the benefits of diversity combining is by using a rake receiver. So rake receiver will have multiple receivers, a rake of receivers in so to say. That's why it's called rake receiver. So it will have multiple receivers, and these receivers will be combining them according to a ratio, giving them weights and combining them. We'll be starting rake receiver in 2 minutes. Today I'm ill, so I have to frequently take breaks, or else I cannot go on. So I'll take 2 minutes. After that, I will again start. So we will look at the rake receiver now. So a rake receiver provides path diversity by coherently combining multipath components that are often present. So a rake receiver's main task is to ensure that the multipaths, when they are combined, see any receiver, when the multipath signals are coming, they will be combined anyways. But the particular task of the rake receiver is to provide a coherent combined framework such that the signals are coherently combined. So they will detect the phase and they will coherently combine the multipath signals so that you can use the multipath components to your advantage to boost your SNR rather than letting them destroy your signal. The receiver is the standard type for direct sequence systems used in mobile communication. Consider a multipath with frequency pairing, selective pairing slowing enough that its time variations are negligible over signal interval. So it is having a frequency selective slow pairing. So there is not much Doppler, but there is a frequency selective fading. To harness the energy in all the multipath component, a receiver should decide which signal was transmitted among M candidates only after processing all the received components. So it will try to detect the main signal from the horde of signal multipath components it has received. Thus, the receiver selects among the M baseband signal of complex envelope. Okay, so more complex envelopes. So it selects the signal with the best number, best yeah, and then so it will identify the best signal and it will assign phases with reference to that signal to the other multipath components and add them constructively. So for this to happen, the multipath components should be okay. So a necessary condition for there are at most so if there are three resolvable conditions, the necessary condition for them to be resolvable is that they should have distinguishable matched filter outputs. So one's matched filter output should not overlap onto another. So that much amount of separation should be maintained among the components. Okay, so this is the receiver. So it takes the signal pulses one by one and all of them will have a particular delay. So each delay signal is processed together and their weights are given and they are combined together to give a rake receiver. So basically you have matched filter detection for all the paths. Okay, further details of rake receiver can be found in the NPTEL analysis. Right now we will be not going much into rake receiver and instead we will start CDMA from the next class. So today's class will be till this only. Thank you.